Complex 3 of the mitochondrial electron transport chain, which is also known as cytochrome BC1, catalyzes the oxidation of fully reduced coenzyme Q by cytochrome C, while concomitantly pumping protons across the intermitochondrial membrane. The mechanism by which this occurs is known as the Q cycle. Complex 3 from bovine heart mitochondria is a dimer of 11 different protein subunits. The central membrane-spanning subunit is cytochrome B, which contains two B-type heme groups, hemes BL and BH. 3 subunits attached to the matrix end and several other transmembrane subunits surround cytochrome B. The iron-sulfur protein, or ISP, contains a 2-iron 2-sulfur cluster known as the Risky center. Another cytochrome, cytochrome C1, binds at the intermembrane space in close proximity to the Risky center of the other monomer. Thus, complex 3 is not fully functional until a dimer forms. It will be easier to visualize the electron transport process if the protein complex is a single color. The redox centers are buried inside the protein, as you can see if we make one of the monomer surfaces partially transparent. We've exposed the redox active components, the hemes and the iron-sulfur cluster. In this presentation, the molecular details of each step in the schematic diagram are reproduced in the molecular model. You can investigate any step by clicking on the numbered step in the diagram. At any point, rolling your mouse over a component in the figure will highlight the corresponding component in the molecular model. To proceed sequentially through the entire exploration, just keep hitting the play button. The molecule that delivers electrons from complex 1 and complex 2 to complex 3 is coenzyme Q, abbreviated QH2 in its fully reduced form. The complete cycling of 2 electrons through complex 3 involves 2 different coenzyme Q carriers, each carrying 2 electrons. One becomes completely oxidized, whereas the other is regenerated in its fully reduced form. The complete Q cycle can therefore be split into 2 cycles, each following the reactions of one of the coenzyme Q molecules. QH2 binds to the QO site on cytochrome B in between its bound heme BL and the 2-iron 2-sulfur cluster on the ISP, where it can interact with both redox centers while still being close to the intermembrane space. One electron from QH2 is passed to the iron-sulfur cluster. In this oxidation, QH2 loses 2 protons, which diffuse into the intermembrane space. The electron moves to the heme of cytochrome C1, and finally to the heme of the next carrier, cytochrome C, which is bound to complex 3 at the surface of the intermembrane space. Reduced cytochrome C then diffuses to complex 4, to which it delivers the electron. Coenzyme Q is now in its radical state, abbreviated Q dot minus. The second electron from Q dot minus is transferred to heme BL, leaving coenzyme Q in its fully oxidized state, abbreviated Q. The oxidized coenzyme Q diffuses through the membrane towards the matrix side, where it binds to a second site, QI, on cytochrome B, adjacent to heme BH. In the meantime, the electron on heme BL is passed to heme BH. Cycle 1 concludes when coenzyme Q at QI is reduced to its radical state by the electron from heme BH. To summarize so far, 1 electron from QH2 has been passed to the next carrier, cytochrome C, and 2 protons have been expelled into the intermembrane space. The second electron lost by coenzyme Q at site QO is returned at site QI. The second cycle begins exactly as did cycle 1, but with a second fully reduced coenzyme Q molecule. The new coenzyme QH2 occupies the QO site. As in cycle 1, 1 electron is passed through the iron-sulfur cluster and cytochrome C1 to a bound cytochrome C, while 2 more protons are released into the intermembrane space. The radical coenzyme Q becomes fully oxidized as it passes its second electron to heme BL. This oxidized coenzyme Q can now return to complex 1 or complex 2 for another pair of electrons. The second electron is passed on to heme BH. The second electron eventually finds its way to coenzyme Q radical, bound at the site Qi. The resulting fully reduced coenzyme Q is released, effectively replacing the coenzyme Q borrowed from the pool at the beginning of cycle 2. These two cycles can be summarized with three equations. The first, fully reduced coenzyme Q, loses one electron and two protons to the intermembrane space, while being oxidized to its radical form. A second fully reduced coenzyme Q becomes fully oxidized, losing two electrons along with two protons. One of these electrons is used to reduce the coenzyme Q radical back to QH2, consuming two protons from the matrix in the process. The net result is the oxidation of one coenzyme Q with two electrons and four protons being delivered to the intermembrane space and two protons consumed from the matrix. Thus, in the Q cycle, the oxidation of one fully reduced coenzyme Q molecule drives the transport of four protons from the matrix to the intermembrane space, whereas in the absence of the Q cycle, only two protons could have been transported in this manner. Since the free energy of oxidation of fully reduced coenzyme Q by cytochrome C is captured by the generation of a proton gradient across the inner mitochondrial membrane, the Q cycle doubles the thermodynamic efficiency of this process. The proton gradient is then dissipated in a manner that drives the synthesis of ATP.